Today we're going to find out what exactly happens to soda cans when they drop into the ocean. Let's go. Hello. After the long Christmas break, I had this pack of Coke left over in my pantry, which I need to get rid of. And I know in the past you guys have requested that I test the soda cans, so I figured why not crush a can with a can. But instead of just doing one quick test and making a short episode, I figured why not propose a question? And if you guys answer correctly, I'll give you a prize. What do you folks think? You all play? All right, let's play Who Wants to Be a Coke Addict? Here we go. All right. So our first contestant is you, and you come from somewhere on this planet. How are you feeling? A little nervous? Ready for your first and only question? Okay. Which of the following would dive the deepest before failing? Is it A, a Coke thrown off New York? B, a shaken Coke thrown off New York? C, a Coke thrown off Kuwait? Or D, Neymar Jr.? Now, you only have one lifeline, so you can call a friend or not. Oh, okay then. I guess that's your final answer. Let's run through the experiments to see if you're correct. What the? How'd they get in there? For those of you who answered C or D, congratulations, you're correct. Here, have some sugar water. And for those of you who are wondering what the heck just happened, stick around. Welcome back. In order to explain what just happened, we'll have to take this can and slice it this way to get a cross section and zoom in. So we'll follow the can as we drop down. In the beginning, the can has an internal pressure, and that's in order to keep the carbon dioxide dissolved in the liquid. So the internal pressure is actually greater than the external pressure, and because of that, there is a perpendicular force acting on the inside of the can wall. And when we zoom into a segment of the aluminum can, which is only 0.1 millimeters thick, by the way, the force acting this way is actually tension. So the whole circumference of the wall is actually under tension, which prevents the can from bursting. And this force over area is called radial or hoop stress, acting in this direction. And at the same time, we also have longitudinal or axial stress acting lengthwise. At one point, the internal pressure would equal the external pressure, and that would be as if you open the can at the surface and empty its content. There'd be no force acting on the wall. But once we cross that point, the external pressure will be greater than the internal pressure, and because it's spherical, there's going to be a compressive load radially and longitudinally. But because it's a thin wall and there's undulations and dents along the surface of the can, what's going to happen is it'll begin to press, and then at the dent, it'll begin to buckle immediately. And once that happens, the internal pressure would go up and eventually equalize with the external pressure. At the same time, the gas content would compress. And it will compress to a point where the volume would be really small until all that's left is the liquid with the dissolved gas. And because the liquid is incompressible, it doesn't crush any further as we drop into the abyss. Now I reckon that most of you answered B for that question I proposed earlier. Doesn't the internal pressure go up after you shake the can? Well, if you think about it, after you shake the can, nothing much has changed. The contents are still the same. The volume is still the same. The temperature is still the same if you don't heat it or cool it. And the pressure is the same. So what's going on? What's going on is when you shake it, you're actually mixing the gas and the liquid further, causing microbubbles to be suspended in the liquid. And these bubbles cling onto the imperfections along the liner of the wall. And what happens when you open the can and break the seal? The pressure is going to drop immediately. And if you go back to Boyle's law, which we learned in episode 3, as soon as the pressure drops, the volume is going to increase rapidly. And that's going to cause this gas-liquid mixture to foam up. And once that happens, it's going to expand and jet out through the small opening and cause a sticky mess everywhere. In the unshaken can, most of the gas is actually on top. So when you crack it open, it's just going to escape and nothing happens. So why did the can in Kuwait go deeper then? Well, that's because it's hotter there, of course. For test A and B, they're both conducted at a lower temperature when compared to test C, which was conducted at the hottest temperature ever recorded on the surface of the ocean. So why does the temperature increase the pressure in the can? For that, we'll have to go back to the year 1808, when the French chemist by the name of Joseph Louis Gay Lussac, while making several daring research expeditions 7,000 meters up in the sky in his hydrogen balloon, collecting air samples, measuring data, and probably struggling to breathe with his good buddy John, discovers the direct proportional relationship between pressure and temperature for gases. That is, as temperature increases, so does pressure, and vice versa, as long as the mass and the volume remains constant. Amazingly, his world record ascents remained unchallenged for 50 years. And yeah, I'm surprised the balloon even got off the ground with spheres of steel that big. Luckily, he survived to publish his findings, one amongst many other findings. And that brings us Gay Lussac's law, which is also expressed as P1 over T1 equals P2 over T2. So what's happening when the molecules heat up? What happens is that the molecules increase in kinetic energy, and that increases their speed at which they travel. And when that happens, more collisions occur between the molecule and the inner wall of a fixed container. And when the collision occurs, it creates a force, and that force over an area is what creates the pressure. Since all three cans survived the plunge and are still sealed, I'm going to try and measure the internal pressure of each sample. I slapped this thing together with a pressure gauge, needle, silicone plug, and some Vaseline. Let's see if this works. I'll need to press this up against the bottom of the can to get a good seal. If there are any kids watching right about now, close your eyes. Sorry, Santa. Oh, shit. Okay, I guess that sort of worked. This measurement, by the way, is by no means accurate. It's just to give us an idea between samples. Let's measure the temperature on sample B, which I forgot to do on sample A, but they're chilled together, so it should be the same temperature, roughly. And let's shake it again for good measure. Okay, here we go. That's much better. Last but not least, we have sample C, which has been sitting in this hot Kuwaiti water. Huh. Looks like it was too hot. It's interesting, it's still sealed. I'm just gonna go ahead and measure the pressure inside. It's probably gone down a bit because the volume has expanded, but just get a rough idea here. Oh yeah, much higher. Good. That was cool. That's hot. Before you guys go, I'm just going to do one last quick pressure test to see the effect on buoyancy, because I know someone out there is going to ask about it. You know what, if you guys don't mind, I'm just going to go to town with it. Well, that was a lot to unpack. I hope you guys learned something new. I could have kept talking, but I didn't want to put you guys to sleep. Please crush the like and subscribe button here and here. And yeah, remember folks, don't forget to recycle. We'll see you next time.